All right. Okay. Hi, folks. Welcome back to day 2 of the GMT NAVCO workshop. I'm glad you're still with us. We had a fun session yesterday, I think. I had fun, at least. And we will continue today with more of the same, although we're going to be moving a little bit more into more advanced topics. No longer just plotting lines and points and text and so on, but going into more geodetic information and how that's plotted in GMT. And then we'll have a little bit animation, and then we'll do some final project. That the way we're going to do the final project is that you're going to work on them, and then there's I think it's a week or so, I can't remember the dates off the top of my head, where the final project due on Slack. And when you post your final project on Slack, that is when we know that you have completed the course. All right, we're going to remind you about this. All right, so we're going to follow the same recipe as yesterday. We're going to have individual instructors give a little overview demo thing of the stuff that is about to be presented, and then we're going to break up into breakout rooms and work on group projects together. And then we have an actual break where we get some food or sleep or coffee or whatever is needed, and then we continue. So we're going to start all the sessions on the posted times, but we might go long on some of them, right, because of the generous breaks and what happens during the presentations. All right, so enough of me babbling along. I'll pass it on to Dong Dong, who's going to kick us off with seismology. Take it away, Dong Dong.
Yeah. Hello, everyone. My name is Dong Dong Tian. I'm a seismologist. I'm currently a postdoc at Michigan State University. In this session, I will talk about how to use GMT to plot beach balls for seismology and geodesy research. So this is the material I will use in this session. So GMT provides 4 modules for seismology and geodesy research. The 4 modules are MEC, COOP, Polar, and SEC. MEC is used to plot beach balls on maps, and the COOP is used to plot beach balls on cross sections. Usually, it's a vertical cross section. And the polar means polarity. Seismologists use polarity of the ground motions to determine focal mechanisms. And SEC is used to plot seismic waveforms in SEC format. In this section, we'll only focus on these 2 modules, MEC and COOP. First, I will briefly explain what a focal mechanism is and what beach ball is. And then I will show how to plot beach balls on maps and cross sections. If you are not familiar with beach balls and focal mechanism, I encourage you to watch this video on YouTube. It's only 6 minutes, and it can help you understand focal mechanism and beach balls. We know that earthquakes are caused by the rupture of geological faults. And here is a figure showing a movement of the fault. And these are just 2 blocks. And the two blocks move relative to each other. And the focal mechanism actually describes the movement of the fault. The movement of the fault actually can be described by usually by 3 parameters. The strike is the direction of the fault. The dip is just the angle of the fault. It can be vertical fault or a horizontal fault or a dipping fault. And also the slip, which describes the slip direction of the 2 blocks. Beach ball is just a graphic representation of the beach balls or of the focal mechanism. Here I will show 3 basic faults, like the strike slip fault, the normal fault, and the reverse fault. So like I will take the strike slip fault as an example. So these are 2 blocks of the fault, and the arrows show the movement of the 2 blocks. You can see that this block goes to this way, and this block goes to this way. And because the movement of the fault, the material of this part and this part will be compressed, and this part, material at this part and this part will be extensional. So we can paint the compressive part by a dark color like gray or black, and we can paint the extensional part by white or light color. Then you can see that for the 3 different different faults, the beach balls are totally different. So if you have some experience with the beach balls and the focal mechanism, actually you can read the beach balls and then you can know the geometry and the movement of the fault. I won't explain too much detail because this is more mainly for geodesy. Here I will use these three focal mechanism as the example data in this session, and this data actually contains 8 columns. The first 3 columns are the longitude, latitude, and depth of the earthquake, and then strike, dip, and rake of the earthquake, which describes the focal mechanism. And the 7th column is the magnitude, which tell us how big the earthquake is. And the last column is the title, just the label for this event. We will use this example data. Let's first copy this file, copy this 4 lines and into a plain text file. I will create a new file and paste this data and save it to a file called mecha.dat and save it. Okay, if you run ls, you will see that we have the file in this directory. Then I will show how we can plot the focal mechanisms in this data file. I will create a new file and then save it as let's call it beachball.sh. With like what we did yesterday, we first need to add a shipban env bash, and I like to add a comment plot beach balls maps, and we also need to use GMT begin, and the figure name is just a beach ball, and we will generate a PNG format and GMT and show. So then we'll use the GMT mecha command to plot the beach balls. So GMT mecha. Then okay, before I start to type the command, let's first go to see the documentation of mecha. Then we'll go to the terminal, run GMT docs mecha. So this is the documentation for the mecha module. We can see that we need to provide the data. So we give it here, mecha.dat. We need to give the projection, the region, and also the -s format. Here we can use Mercator projection, and the size of the figure can be maybe 10 centimeters. And we also need to give the region of the map. We can run GMT info mac.dat. Then we can know the minimum and the maximum for the longitude and latitude and depth. So this is a range for the longitude. This is a range for the latitude. We can choose a value like 110 and 120 for latitude, and maybe 35 for latitude. So this is just we already did this like yesterday in base map and the coast. We also need to add the -b option so we can have the frame. So the most important option in mecha module is -s. So -s option actually determines the format of the input data, and also it controls the size of the beach balls. There are many different ways to describe a focal mechanism. We can use a strike deep rake to describe a focal mechanism. We can also use a symmetrical 3x3 moment tensor to describe a focal mechanism. In this tutorial, we'll use the simple one, the -SA. So we use -SA here. It means that we need to provide the longitude, latitude, depth, strike deep rake, and the magnitude. Then we can give the scale, the size of the beach ball. Here we use a size like 1 centimeter. This size is the size for the magnitude of 5 earthquakes. And for smaller earthquakes, the beach ball will be smaller. For large earthquakes, the beach ball will be larger. Then we save this file and run the script bash beachball.sh. Okay, use this simple command. We now have the beach ball on maps. The x-axis is the longitude, the y-axis is the depth, and all the beach balls are plotted at the location of the earthquake. And you can see that the size of the beach ball is different because if you look at the data, you will see that the 3 earthquakes have different magnitude and the size are different. If you want to, sometimes you may want to have to plot the beach balls using the same size. You can use the -m option. If you go to the documentation of Mecha module and click the -m, you will see that use the same size for any magnitude. We can try here -m. -m. Then we can save this file and bash beachball.sh. You can see now that the beach ball size are the same for all the earthquakes. By default, the compressional quadrant is painted by black, and the extensional part is colored by white. We can also change this color. I will remove the -m option here, and the compressional quadrant can be, the color of this compressional part can be controlled by -g option. We can give a color like -g red, and the extensional part is controlled by the -e option. We can give a light color like -e light blue. Okay. Okay, now you can see that actually the map looks better compared to the white-black figure before. So -g and -e can be used to change the colors. If we look at this figure, we can see that what we can learn from this figure. We know the location of the earthquakes. We know the focal magnetism of these earthquakes, but we still don't know the depth of the earthquakes because there are no depth information in this 2D plot. What we usually do is we can color the compressive part by different colors, and the color can be determined by depth. And this can be done by using the -c option. So if you click at the -c link here, and you will see that you need to give a CPT file and then let the compressive part color be determined by the Z value in the third column. That's the depth of the earthquakes. I will comment out this line and copy paste to a new line. I'll also remove the -g, -e here. Okay, so we need to use the -c option to color the beach balls by depth. But before that, we need to create a CPT file. We can run the GMT make CPT and then -c. We need to choose a master CPT. So there are many CPT files in GMT, and we can run GMT docs home, which can open the homepage of the documentation. So there is a link here, building CPTs in the quick links. If you click this link, you will see that there are maybe 70 or 40 CPT files in this page. I will choose like maybe this one, hot, -c hot. I will choose this one as the master CPT, but I still need to give the minimum and the maximum depth range for the earthquakes. In this data, if the depth range is the minimum depth is 50 kilometers and the maximum is 45. So we can have a depth range like from 0 to 45. So this command create a CBT file from 0 to 50. And now we, in the Mecha command, we use the -a option to use this CBT file. If we run this script, we'll see a figure like this one. You can see that now the beach balls actually have different colors, and the colors are determined by the depth of the earthquake. Of course, we still need to plot a color bar so that we know the meaning of the depth. We can use GMT color bar. Okay, so we can see that the dark color, like the dark right, is shallow earthquake, and this color, the light color, is deeper earthquakes. I usually like to plot the color bars on the middle right of the map, so we can use -d J middle right, which will plot the big color bar at the right of the map. And I want to use -b plus L to add a label to the color bar, depth kilometer. Okay, so now the map looks much better now. And from this figure, we know all the information about the earthquake, the location, the depth, and the size of the magnitude, and also the focal magnetism. So that's all about the Mecha command. And I will next go to the Cooper command. So Cooper command is used to plot beach balls on cross sections. Usually the cross section is vertical, a vertical cross section. Like in this example, I can draw a line here. No, how to draw a line? Okay. I can draw a line from here to here. So this is a cross section starting from here to here, and it's a vertical cross section, and we can project all the earthquakes to this vertical cross section. There are multiple ways to to specify the cross section. You can just give the starting point and the end point of the cross section, or you can give the starting point, the azimuth, and also the length of the cross section. Okay, now before we go to the coop command, I will create a new file, new script. Let's go to new file and save it as cross-section.sh. Okay, we still need to add this information and add a comment line, plot beach balls on cross sections, and GMT begin cross section PNG figure GMT and show. Okay, now let's go to the terminal and type GMT docs coop, and it will open the documentation for Cooper modulus. You can see that this modular is actually very similar to the Mecha modular. It still has the -s option, -e, -c, -m, -g, and the -e options. So they are very similar. The main difference is the -a option, which which determines the cross sections. We'll go to this script and type GMT coop. The data is mecha.dat. And we want to have a frame -b af, and we need to specify the input data. So we still use -sa1c, just like what we did with the Mecha modulus. We need to use the -a option to specify the cross section. And there are, as you can see here, there are 4 different ways to specify the cross section. We will use this one, -a, and -a, capital A, small a. And then we need to give the starting point of the cross section. Here we can choose 111 slash 33, and then the end point of the cross section, maybe 119 and 33. So it determines the starting point and then the end point of the cross sections. There are also some modifiers to this -a option. The +d controls the deep angle of this cross section. Usually it's a vertical cross section, but it also can also be a horizontal cross section or a deeping cross section. By default, the deep angle is 90 degrees. It means that the cross section is vertical. And the +w modifier controls the sets the width of the cross section. It means that it means that if we want to include all the earthquakes away from this cross section, so if the width is infinity, the default value of the width is infinity. It means that we will include all the earthquakes on each side of the cross section. So if we set the width to maybe 100 kilometer, it means that we only have earthquakes 100 away from the cross section, and any beach balls far away from this cross section will be just ignored. And there is also a modifier +z, which can limit the depth range of the earthquakes. Here we can use +z. The minimum depth is 0, and the maximum depth maybe 50 kilometer. So we can include all the earthquakes, all the 3 earthquakes. Usually we need to give the region of the map. When we plot a depth cross section, the x-axis actually is the distance along the cross section, and the y-axis is depth. So we need to use a linear projection -jx. The width of the projection is 10 centimeter, and the height is, we can give it a 5 centimeter. And we should also use give the -r option, but it's difficult to give because the x-axis is the distance of the cross section, but it's not easy to calculate the length. And so GMT provide a modifier called +r to the -a option, and it will automatically determine the length of the cross section and also the depth range of the cross section. So we don't need to give the -r here. Let's say, okay, we can try to run this script --cross-section.sh. Okay, so here is the figure. Let me see. Okay, so this is a depth cross section for all the earthquakes. The x-axis is the distance along this cross section. Here, 0 kilometer is the starting point here, and this is the end point at here. I think we need to change the -b settings because we want to have more labels for the x-axis and the y-axis. We can use -bx. I will add a label, distance kilometer. And for the y-axis, -b or plus L, no, plus small l, depth kilometer. cross-section.sh. Okay, now it's clear that this is the distance and this is the depth. And you can see that actually the frame is not large enough. The region is not large enough. So this part is cropped. Now we can manually set the range 0 to 700 kilometer, and the depth range is 0 to, this is 50. We can increase to 30 kilometer. If we run the script, we'll have a, we need to remove the plus R option here. Okay, now it's better. Okay, I need to change this one. Okay, so this is the distance along the profile. This is a depth range. And usually we want to depth increase from up to down, but this is the depth increase from down to up. So we need to reverse the y-axis. It's very simple to reverse the y-axis. You can just set a negative height for this map. We change the 5 centimeter to minus 5 centimeter and run the script again. Okay, now it's better. So this is 0 kilometer, this is 6 kilometer. As I have said that before, the other options, there are many similar options in Mecha and Cope. So we can still use -G, red, -E, light blue to change the color of the Cope command. Cross-section.sh. Okay. So that's all about the Mecha modulus and the Cope modulus. And then before we go to the broad section sections and do the group exercise, we need to learn how to get the focal magnetism data. Okay, so this is our group exercise. We need to plot two figures like this one. This is a map view of the beach balls in the Japan subduction zone, and this is the depth cross-section views. And to plot a data like plot a figure like this one, we need to have the focal magnetism data. We can go to this site, the global CMT site. This global CMT project provides focal magnetism for all the global earthquakes greater than magnitude 5. We can scroll down to this link, the CMT catalog web search. And here you can search the earthquakes. Here you can specify the time range, the magnitude, the locations, and also other informations. Just like here, you can try maybe 2000, the first day of 2000, and you can specify the ending date, maybe 10-year data from 2000 to 2010. And this is a magnitude range from 0 to 10, and this is a longitude range. If we want to plot the beach ball in Japan, we can use maybe 30 to 50. So this is 30 degree to 50 degree, and the longitude will be maybe 120 to 150. Okay, so we specify the longitude and latitude range, and for depth you can use maybe from 0 to 1,000 kilometers. And when you go to the output type, you need to choose the GMT PS Mecha input, and you will click down this button. You will see that all the earthquakes. So this is the information for all the earthquakes in this time range and spatial range. And if you scroll down to the bottom of this page, you will see that there are actually maybe 100 even more earthquakes here. So you need to copy all the data from the top to the bottom. Oh, it's long. Okay, from the top to the bottom, and then create a new file. new file, save this data, and save it to a file like Japan mecha.data. Then you can use this data to plot figures like this one. There are some tips here. In the tutorial, we use the -SA option to specify the format of the input data. But because Global CMT project provide a different format for the input data, so we have to use -SD, -SM, or -SC option to use a Global CMT data. And then, okay, that's all. So that's what I teach about these two modulars. Then we can go to the group sections and do the group exercise. You can choose the Japan subduction zone or any subduction zone or any region you are interested. And here are script to plot these two figures, and you can use this one as a reference.
All right, so it looks like we are back in the plenary session, all of us. That was fun. We found one bug in COOP that the plus Z modifier to -A is required, although it's listed as optional. So we got to work on that.
And I was not able to help. Someone was having a problem with COOP because, well, I was able to help up to the point that the errors disappeared, but the plot was still blank.
Okay, let's continue that in the Slack. We should be able to do it during the background, I guess, because we got
the same error in our group as well.
Yeah.
We're just doing that and then got pulled back to this main session.
Yeah.
Oh, okay, yeah, I was trying to, but so okay. You have many people with maybe not the same issue, but
okay.
Family.
So maybe Joachim, you can post that to Slack to everybody too, so we can sort of look at that because Eric's not going to be busy with other things.
It's not me. It's she's listening. I don't.
Okay. We'll blame Dong Dong for this, of course. There's something there ready to look at.
I told her to put it on Slack, but we kept talking, so she had no time.
Yeah, that's fine. Because we got to march on, relentlessly here, and it's past 8:15, so we're going to switch gears slightly to go to the geodesy session, which Eric is going to present, and he's given instructions in Slack that we should download a tarball first with support data for some of the exercises, I believe. So Eric.
Yeah, like the GNSS data and some grids.
Yeah, so you can take it away, Eric.
All right, let me share my screen. Can everyone see my screen?
Yeah.
All right, great. So this session will be plotting. I mean, it's called geodesy session, but actually geodetic data is composed of all kinds of data formats, like data points or lines or grids or even movies. I mean, if you have already taken the course from yesterday where Leo and Zhuangqun talked about like plotting symbols and grids, you are actually able to plot most kind of data set, and geodetic data is no exception. But today here, we're only going to be plotting one type of the geodetic data, which is mostly associated with GNSS data here. And before we start, I hope everyone's able to get to this page and click on this link and download the supporting data set, in which there will be like some grids, like deformation grids, and also GPS data and some fault traces that we'll be playing with today. All right, let's get started. So for this session, there are mainly two topics. One is trying to look at one of the options in GMT that is mainly associated with the GMT reload command with the -SE option for plotting vectors. And I'm going to go through all these options or attributes during this session and show you guys some of the examples. And then after that, we'll be mainly trying to plot a vectorized deformation field associated with the ridgecrest earthquakes as an example. So let's first go over some of these attributes on these vectors. So the command that you'll be using is GMT below with the -SE option. This option allows you to plot arrows with uncertainty ellipses. Followed by these attributes are like velocity scale, confidence level, and then the font size. The font size mainly controls the site name. And for this option, the required input asks for several columns of data. Longitude, latitude, your east and north velocity, east and north uncertainty, and their correlation. Of course, you can append a site name at the end, or you could just leave it blank. And when you are plotting this, it's going to give you a line directing from this longitude, latitude with that size on your map. But what really controls the arrow is actually the one of the options here is the -A option. Of course, after that, you're going to append the size, determining how large that arrow is. And with other attributes appending at the end, I'm going to go through each of them. For example, with the A, you can change the apex, like you want a wider arrow or like a thinner arrow. Also with +BEM, it represents placing an arrow at the beginning, end, and middle, with TCAI representing for like terminal line, a circle, an arrow, or tail. Also, if you want the arrow to have some color, you can use a +G with a color, and the +P changes the pen or the outline of those arrows or tails. You also noted maybe for this option, you have another one that's a -W, but generally this controls the entire thing, including the uncertainty circle and also the segment, the line segment. You can also choose to plot only half of the arrow, whether it's left half or right half. And you could also choose to normalize the entire data set. Next, we're gonna try every single one of these experiments, these options, and see what it does to the data set. All right, let me stop sharing this tab and share again this VSC. Can everyone see this screen for now?
Yes.
All right, great. So you probably already downloaded this data set, right? I mean, if you just uncompress it, you have a bunch of files in it. So we'll be playing just inside that folder. All right. So here we are in this folder. And to start the plotting, let's do this GMT --new. I do this all the time, but maybe let's call it plotwec.sh. Then you see that there's a new file that got generated in this folder. If you open that, it kind of looks like this. I mean, the only thing that I need to mention here is that you don't necessarily have to have this first part, because my default shell is C shell, but here we're going to use bash. So I'm just going to delete it for now. And let's choose a figure name. Let's just call it vector. And in the format of JPEG. I don't want it to show up. But like what we did yesterday, at the very beginning, we always want to create something to be plotted. So here is no exception. And we're going to use the echo command again. Let's say that we want a vector from 0, 0 with the size of 1, 1. So basically 45 degrees pointing northeastwards. And then for the uncertainty, for now, we're just going to put in zeros. Then we redirect the plot to something maybe like temp.dat. Also, I mean, we are doing this kind of shell scripting. It's always good to set variables. And here, we're going to set what we call maybe projection, range, and frame. Let's say that we want it to be Cartesian in scale, 3/3. That's the size of the map. And since this is a really tiny arrow, so we just want to, for example, the range from -1 to 2, 2, -1 to 2. And for the frame, I kind of want annotation and grid line and frame every 1 unit. So that will be our variable here for setting the boundaries. Next, we're going to use GMT reload command. So GMT reload, and the file name is temp.dat with $JRB. That's what we specified at the beginning. Then we're going to use this -SE command. So for now, I'm going to just plot the full scale, which is 1.0. That's the number I think that's going to get multiplied to your data set. And then we're going to specify maybe like 1 standard deviation, maybe 1 sigma, which is 0.65 confidence level. And we set the font size to be 10. And also for the width, how about 1 pixel for now? If we save this file and go back to our terminal, and hit bash plot.sh. Oops. No module name. Oh, I mistyped. Willow. Now we get a plot here. If you open that, you have an arrow from 0, 0 to 1, 1, right? Let's split this into 2 columns. So you have the script on one side and the plot on the other. Next, we're gonna see like, what if we put in some uncertainty to this arrow? If we go back to the script, for example, if we change it to 0.2 and 0.2, so this is the standard deviation for the uncertainty, right? And 0 here means the correlation between the two are 0, which means they are really independent with each other. We do this again, you'll see it's going to give you a circle on this plot standing for the arrow. We could also choose maybe a higher confidence level. For example, we want to do a 99, which will be like 3 sigma, 3 times the standard deviation. Then if you do this same plot again, you see that the circle is getting larger, almost 3 times larger, right? We could also say that the error from the east and the north component are kind of correlated. Let's say that it's 0.5 correlated. If you do this, the circle changes to an ellipse. We could also say that maybe I want it to be anti-correlated. So when the error increases in one direction, it's changed it, in the other direction. So you have an ellipse that's sort of aligned with the negative 45 degrees. All right, we pretty much played with this data set a little bit. Next, what we're gonna do is to play with the -A option, which stands for the arrow attributes. Let's do a backslash. And what we want to do is with the -A option, for now, the size of the arrow is just the default. Let's change it to maybe like 20 pixel. And then we want it to be at the end of the segment with an arrow. Of course, the uppercase A, it stands for a plane arrow. If we do that, you see that it changed to a plane arrow. It doesn't look so good, so we're going to change it to a fancy arrow, which is a lowercase a here. Now it's a fancy arrow. Of course, there are many other options you can play with. For example, I want at the beginning of the arrow, there is an arrow tail, actually. So we just type in +bi. We do that again, and now you see that there is a arrow tail at the beginning. Also, what you could do is that, what if we say that we want the arrow to be with a different color? Let's say we want a red color to fill this arrow. Then you have the color change to red. And you can also change the, for example, the apex, we call it. The default is about 30 degrees, but I wanted my arrow to be maybe a little bit fatter. I want it to be 70 degrees. now you have a fat arrow. Note that this option not only changes the arrow head, but also the arrow tail. Whatever you specify at the beginning, end, and the middle, this parameter actually affects all of them. The final one, let's say, or maybe the final two. For example, I want the width of the lines for this arrowhead and arrow tail to be maybe 5 pixels. Then you see the surrounding line actually got changed, right? It's becoming thicker. Another example that we could play with is that I only want for example, the left half of this arrow. Now the other half disappears. So you could play with all these parameters when you're trying to plot a vector. And of course, this input data set, it could be like multiple lines, have like maybe thousands of arrows in it, and it's going to produce it in the map simultaneously. All right, we already played with these attributes. Next, we're going to play with some real data sets. That's for the ridgecrest earthquakes. But before that, what I'm going to do is that let's go over like each of these files first to see what's inside the data set. So the first one will be this gps.dat. In it, add gps.dat. You see it has longitude, latitude, and its deformation. I think they are in centimeters, if I remember right, or millimeters. Of course, you may realize that the following 3 numbers actually made up by me. I'm just putting 1, 1, and 0.5 just as an experiment. If you want the real data set, you can get it from UNALCO for sure. The next file is these grids you see here. This de.grd and dn.grd represent the eastward deformation and northward deformation from a source model. The source model is inverted from other geodetic data like the GNSS data here, and also INSAR data. This is kind of like the forwarded deformation field from that source model. If you do a GMT GRD info on one of them, you see some of the information like what's the region of it, what's the increment, and the minimum and the maximum value of this grid. The next one is the dem.cpt. Actually, there are a lot of default CPT files in GMT. If you are not satisfied, for example, you're really picky about these CPT files, you can also generate your own, or you could go to a place called the CPT City. Over there, they also have a lot of CPT files as well. You can download and manipulate them using GMT. The next one is called dem_dsam.grd. This one is the digital elevation model over the region of this area. You can also use the Earth relief data provided by GMT for sure. I'm only attaching it here because this is relatively a small area, and I don't want everyone to be trying to fetch data from the same server at the same time. The next one is called new faults.gmt. These are actually like fault segments that's being detected by like INSAR data and optical data specifically for this earthquake. If you do a head new faults.gmt, you see that this file is actually composed of multiple segments separated by this marker. So GMT allows you to like create a file that contains like maybe 1 million segments in it, as long as they are well documented. So over here, all of them are being named as untitled paths, but for each of them, you see that it starts from here, then march to the next point, and then the next point. I think that's pretty much all of it. So for now, we're going to start plotting using this data set. So again, let's do a GMT -new script. Let's redirect that into, how to say, plot map. And then we're going to open that right here. change a little bit. If your default is bash, you don't need to do anything except changing the session name. All right, let's call this figure, just call it map, maybe. Don't want it to show up. Like before really start, let's set some variables for this plotting. So the DEM, let's say DEM file will be the DEM underscore dsam.grd, which is this file here. And next, we're going to have the GPS that equals, what's the name of the file? gps.dat. Now we're going to try to figure out the plotting like bounding box. There's a really handy like way of determining this if you have a grid ready to be plotted, which is, of course, you can use a $ with a bracket like that. But here I'm going to use a strange code. This is actually the key that's next to your number 1 on the left, which is really handy. What you can do is that you type in GMT GRD info on your DEM grid with a -i- option. We can try this in this terminal for now and see what it really gave you. So first, let's set the DEM as this. Oops, I mean C shell. And if you echo $DEM, it'll tell you that this is what's being set for this variable. And if you show this part of the command to the terminal window, I'm mistyping. GMT GRD info, I'm sorry. What it gave you is actually the range of this grid. It matches the GRD info like from this grid file, but it's in a format where you can directly use for other plotting. Of course, you can also choose to use a -r, then attaching that grid. It also gave you the range. I think it's a handy feature for the new GMT. Next, we're going to set the output to just a file name. Maybe we already said it's called map, so we're just going to keep it as map. Then the format, let's say we want a JPEG file. A good reason for doing all these variables is that that later on when we are going to come back and you have a really complicated script, then you know where to change all these variables. You don't have to go through a really lengthy script. So the output is map, then your format. And now we're ready to go. So the first step, as always, is to plot a base map to see whether it produced anything that's reasonable. What we're going to do is GMT base map. I want a size to be J vector projection with 6. Well, set 6 is okay. It's not too large. Then your $RR, which is the range. Then we're going to BAF. We're just going to let the program to determine like what's a good spacing. Then if we hit, or hit this bash plot underscore map.sh. All right, there's a map.jpg getting produced in your folder. If you open that, I mean, there's nothing in it. Again, let's do this in a 2-column way. So you'll see the changes in this map. All right, now we have a base map. Next, we're gonna add ingredients to this. We're gonna plot the DEM. What we're gonna do is, as we learned yesterday, GRD image, your $DEM, which is the digital elevation model for this area. I also want some shading for this area, so it looks nice. And the color table, I'm going to use what's inside the folder, which is dem.cpt. Let's see what it does. All right. dem.cpt maybe is not too optimized for this region. It's not Ice Age, but seems it's all covered by snow. I don't want that. So we're going to change this CPT file. What we're going to do is run this again, GMT make CPT, right? dem.cpt. And we want the axes to be maybe 0 to 3000 with an interval of 500. And then I also want it to be continuous. I want it to saturate with -d into, I don't know, temporary.cpt. Then we're also going to change this file in your GRD image plot. After that, you save the file and you try this command again. Oops, something went wrong. No input file expected. Oh, it's minus. Oh, I forgot the -c option. Sorry. You had to specify this as a color table. So you need a -c dem.cpt. Okay, now it looks much nicer. Except seems the shading is kind of strong. Like, because I'm going to plot a deformation field on top of it, I don't want it to be so bright and so eyeball taking. Let's change something. So this -i option, it actually allows you to append like attributes. So what we're going to do is that we're going to normalize it with exponential method. For example, I want the scale factor to be 0.3 or maybe 0.4. I don't know. You can always come back and change that number. If we do that again, and now it's becoming less bright. I mean, the shading becomes weaker than before, right? Now we have this DEM. You may also realize that this is somewhere in California. That's San Andreas. This is the Garlock, and the Los Angeles is over here. But next to Los Angeles, that part should be an ocean, right? But now it's plotted as green color, which is not really the case. So what we're going to do next is that we're going to do a coast command that we learned yesterday with -NA. So we're going to plot all the borders, including country borders and state borders, with, for example, 0.5 pixel and in maybe black colors. And we want the type of this plot to be dash. And we're going to fill the ocean with light blue colors. And also for the coastline, because this is a really small area, we want it to be in full definition, which is -df. If we save this again and you make the plot, okay, so the ocean becomes light blue. And you also see this little lake over here as well. It's also becoming blue. The next we're gonna do is plot the deformation data on top of this beautiful map. You know, GMT is really powerful in plotting, but GMT is actually more than that. It's also able to handle these gridded data in a really like handy fashion. In terms of processing data, it's also very efficient because most of the modules are written in C. So what we're going to do is that we're going to take the data that's already in this folder, that de.grd and dn.grd, and sample it into a coarser like table and plot it with GMT. So what we're going to do here is called GMT GRD sample. We're going to sample the grid, which is de.grd with an interval. Maybe I want to plot it every 10 kilometers also. So I'm going to give it 0.1 degrees. Then you specify the output as maybe temp eastward of GRD. we're going to do the same thing for the north component, which will be GMT GRD sample bn.grd minus I.1, then with minus g temp n.grd. Now we have this two grid, but you can't really directly plot this into vectors. Remember that the below command asks you to input tables. So what we're going to do is that we're going to convert these grid into tables. And in GMT, there's a command called GMT GRD2 XYZ. So we are going to convert the grid data into longitude, latitude, and values. So give the input temp e.grd, and we're going to redirect the output into temp e.longitude, latitude, deformation. We just call it LLD for now. Do the same thing for north component, temp n.grd into temp n.lld. But you may realize that now we have two tables, but the below command asks only for one table. So we're going to manipulate these tables before we really play the below command. The command here we're going to use is a Linux command called paste. Yesterday, you probably already learned cat, which is concatenate, right? It's going to put these files one after another, but the paste command is actually going to put these two tables side by side. For example, each of these ones are actually a 3-column table. So paste is going to convert it into one 6-column table if you append these file names. Now we have a 6-column table, but we only need, for example, maybe just the longitude, latitude, east and north. We're going to pipe this result into another Linux command called awk. Awk is also really powerful. We're going to print out $1, $2, $3. So this will be the first, second, and third column from this pasted table. So that's the longitude, latitude, and eastward deformation. Next, what we want is a north deformation. So it'll be 4, 5, 6. It'll be $6, right? Now we have longitude, latitude, east and north. Since this is a field we're plotting, we don't need those ellipses to represent uncertainty for now. We're just going to put in zeros. Let me split this. And now we're going to redirect the result into a file maybe called deformation.dat. All right, now we have a table to play with. What we're going to do is do a GMT below defo.dat. As we experimented, we want because this is a field, there'll be like tons of arrows. We want it to be really thin. For example, 0.1 pixel. We want it to be black. Also with minus SE. Also, you may want to note that here is that these values are actually in millimeter or centimeters that are kind of large numbers. You don't want to plot them at full scale. It's going to be larger than your map. So what we're going to do is that we're going to only plot at maybe 0.02 scale. Then the other parameters doesn't really matter, but I'm going to put it here anyway. Next line. Then we're going to specify what kind of arrow you want. We want it to be maybe 10 pixels. Because it's going to be a field, we're going to use plain arrows instead of fancy arrows. If you directly do this, we'll see what's going to get onto the map. Oh, it gives a lot of warnings. It says you probably want to normalize it because this is really crowded. You see all the arrowhead are with the same size. So it's kind of filling up this entire map. So what we're going to do is we want to put this plus n option. For example, we want to normalize it with maybe the size of 10. If we save this and redo your bash command, of course, it's going to warn you that when you're doing this sampling, this 0.1 interval is larger than like the sampling inside this grid. So it's going to warn you, you might have aliasing, but it's okay for now. Now we have a deformation field in the map, right? In fact, in GMT, there's another handy way of doing this plot, which is called GRD vector. It's not exactly like this. I can show you how it is done. So for now, let's comment out all these lines. Oops. There are some differences that you'll be, it's going to show up in the field, but the differences are small. So the command you'll be doing is called GMT GRD vector. This is going to plot the vector based on two grids, the east and north grid. So we give it the de.grd, dn.grd. Again, we want it to be very thin, so it's 0.1 pixels. I think the default is black, so. But this time, when you do the -s option, it's a little bit different. Over here, the factor here is actually the inverse of the velocity factor. We put in a 0.02 here, but over here you have to use 50, which is the inverse. It's just a different setup for these two commands. One is to be multiplied, the other is probably to be divided. And also the attributes of arrow is changed to this -q option, but all the attributes are the same. So we could just copy this line over here. With 10 pixel size, plain arrow at the end, normalized by a factor of 10. And then we redo this plotting. It's taking a little bit longer, which is normal. Oops, that looks awful. Oh, I forgot to specify how much spacing that is needed for this plot, which is supposed to be the -i option. Since we did 0.1 here, we're also going to use 0.1 for this plotting. That's probably the reason why it's taking longer. Now we redo the bash script. It's giving you this. If you play back and forth, you see that this is not really giving you exact the same solution. That'll be one of the bonus challenge to figure out why they're different. But for now, we're just going to continue. So now you have this deformation field that's plotted in vectors. Next, we're going to add the faults to these plot. And what we're going to do is that we're going to use GMT plot. Remember, the file name is called new faults.gmt. And let's say we're going to plot it with 0.5 pixel in maybe, I don't know, red colors. If you save the script and redo the plotting, oh, something pops up in the image. If you make this a little bit larger, you see that these are the segments of the faults from these earthquakes. How can I make it smaller? Never mind, I just reopen it. Right. The final command that we're going to do is to plot the GPS vectors on top of this. Again, we're going to use the GMT below the GPS file, which is the $GPS. Because, I mean, there are much fewer GPS data over here. We're going to plot it with a thicker pin, let's say 1 pixel, with maybe blue colors. And we want to fill it with black. And then the -SE, we want the same parameter as here. So we're going to do the 0.02 and 0.65 confidence level, and with the font size being 10. Next, we're going to do this -A option. Just copy it over, which is a 10 pixel size of arrowhead. But this time, we're going to do a fancy arrow so that they look different from these background deformation field. We're going to do a lowercase a. We're going to normalize them with the same factor.
Black needs a K, black needs a C.
Oh, BLECK. Thanks. I mean, it happens all the time. If we do the bash plot map .sh, now you'll see the GNSS vectors are getting added on top of this deformation field. All right. I mean, this will be pretty much everything for the showcase. Let me stop sharing for now and then go back to the page. So we're up to this plot over here. So during the breakout session, I want you guys to try to accomplish the plot by adding this, for example, the epicenters and also a line connecting to a beach ball that tells the focal mechanism. So this will be part of the bonus challenge. Of course, if you get really bored, say, this is too easy for me, what you could do is that if you scroll a little bit downward, you'll see that there are focal mechanisms illustrated here, but also there is this UNAVCO geophysical event response page. Over there, you can find GNSS solutions for many of the events. For example, if we click on that, it will redirect me to UNAVCO. And if you scroll downward, you see, there are a bunch of these earthquakes. For example, I want to try this one. If you click on it, it's going to show you what it contains from these figures. But what you really want to download is something here. If you say, scroll a little bit downward, you'll see it says gauge GPS GNSS displacement estimate. It says now available. If you click on that, oops, it says opening in Finder. Oh, it's downloaded to my local server. I'm gonna drag it to this. All right, can you guys see this? I mean, it's a little bit too small though. That's the co-seismic offset from a specific earthquake. You have longitude, latitude, east and north, uncertainties there. I mean, correlation is not solved for now. But if you take out these columns, you should be able to plot any of the earthquakes. And you have the Earth relief from the GMT side. So feel free to try any of these. All right, that's pretty much it.
Right, very good. So I guess we will go into breakout rooms, and we have until, let's see here, 1905 UTC to play with this, and then we have the long break, which we can continue to work on these projects.
Yeah, if you guys got any questions, feel free to post it on the Slack chat room, and also if you get nice plots, do share it in the short course channel.
Yes, you forgot to say that for the seismology session too. You can also share your product there.
All set?
Yeah, it is seconds away. So yeah, I think I'm all set. See if you can get some animations going.
Yeah, that's always the most fun part.
Yeah, we'll find out. We gotta think of some new clever example, I think. Spinning Earth is pretty simple and basic, at least to get the idea.
Ooh, could you do like a spinning flat Earth?
Oh, that's thought. Yeah, I just can't do it on the fly here. I gotta spend time thinking about it, So, all right, folks, welcome back from whatever break you had, or meal you ate, or what nap you took. So we're gonna start on the animation section, and I'm actually gonna do some old school lecturing a little bit first to sort of get your mind set on what we are up against, and then we're gonna do some very simple examples and a group thing together. So I'm gonna share my screen. And get this started here. All right, you should see my presentation, correct? Yeah, all right, good. So, okay, so my slogan here is animation for the masses. We should all be able to make animations of our science. If you have things that are moving or time dependent or something, it should be more common than it is. We're going to do very simple stuff today, obviously. You can visit the GMT YouTube channels to see some longer animations to inspire you to do something. And if you make a cool movie, let us know so we can post it up there as well. So in GMT, we use the tools movie and events to actually create these animations. And as you all know, movies are just a bunch of still pictures. So the task is to make the same thing, a bunch of still pictures, and put them back in the right order and make a movie. So there's two time axes here. It's the playback time, which is, how many frames per second are you going to display? And then it's the time represented by each frame. And that could be, millions of years of plate tectonics or nanoseconds or some other thing. So that's sort of user dependent, what you actually are showing, or it could be real time. But usually we have sped up time, right? If you want to make a movie of animation of earthquakes from 2020, you don't want it to take a year. You want to speed it up. So with different time axes. The simplest way to think of making these movies is to think of your plots. And if you stick to the standard sort of movie format, the 16:9 that all our TVs are now, or even the old 4:3 older screens, that's the simplest thing. And then you can think of these page dimensions. So I make most of my movies in 16:9 if I make an HD movie. And then I think in terms of a paper size of 24 by 13.5 centimeter. If I think of that, and then I can lay out my plot as I would a normal plot, and then everything is much simpler to scale into an image. But sometimes you want to make a movie that have a kind of custom size, and you can do that too. But I'm going to stick to some basic, 16:9 formats today. There are a couple of quotes about repetition. So insanity is doing the same thing over and over again and expecting different results. This has been attributed to Albert Einstein, although there's no real evidence that he actually said this. But you kind of heard this kind of expression. And then there's the other one, GMT animation is doing the same thing over and over again and getting different results. And that's been attributed to Paul Wessel, but there's no evidence that he ever said that either. So the thing here is that we want to do the second thing. And the key here is that to use variables. If you don't use variables, we are going to get the same thing over and over again. It will be an extremely boring movie of the same frame playing back. So we're going to learn about variables. So basically what movie does is to take out from your control the loop over all the frames that you got to make. So you basically create a single script that makes a single frame, and then we loop over that again and again automatically. And by using variables, we get different plots each time instead of the same plot. So there are some special variables that movie will maintain for you that will change with each frame. And it's our job to write a script that uses these variables so that we can get the change. You can have a background and foreground. I'm not going to cover that today because we don't have time, but you can do that. And everything else, including parallelizing this operation and running these frames on all your cores, is done automatically. So there's some special variables that are set in the shell for you to use. These are constants throughout the movie, right? So if you really need to know how many frames the movie is composed of or how high the plot width is, and you want to use that in your plot, those are available. You can just use $movie height, for instance, and you have that value. It won't change. It's the same one for the whole movie, obviously. The more interesting things are the stuff that vary. So there's a whole bunch of variables that you can use in your script that are created and updated for you. So let's imagine that we have a data file that has, in this case, 5 columns, 1, 2, 3, 4 columns and trailing text, right? So it has longitude, latitude, a couple of data columns, and then some text. And we have a whole file like this, and we want to use that in our animation. Maybe these are earthquakes or location where we want to show something. When we are making frame number 47, we will be accessing record number 47 in this file. And let's say it looks like this. In that instance, when frame 47 is accessed, all these parameters that you see on the left in my table here, movie frame, movie tag, movie text also, they are automatically assigned. So in this case, the tag and the frame name, those are things with 47 in them because it's the 47th frame. And they will be used to create the file names for the tiles. But then you'll see the movie column and movie word. They will be updated to have the various column entries in the data file for that record. So in this case here, movie call 3 will have the value minus 3,500 because that's the value of that column at that time or that row for that record. So if we write scripts that use these variables, we will get different results each time for each frame because they're going to get updated from your data file. So that's our trick, to use these variables to write our scripts and then just run the scripts again and again and again and let GMT deal with replacing the values. So we're going to try this out on a very simple thing. We're going to make a spinning Earth. So the movie here is the Earth going to rotate around. We're going to use the orthographic projection, which is sort of Earth viewed from infinity. And we're going to let the central longitude that sort of sets the viewpoint equal the frame number. So as the frame goes up, we basically rotate the Earth a little bit by 1 degree. And we're just going to do the first 90 or so frames. And we're going to make a very small movie, like a 360p. So that's 360 lines in the 16:9 format of the movie. And then we're going to play with some of those things to expose some movie option there. So I'm going to stop this share and presentation, and we're going to start playing with this thing here. So I know you can't see my screen yet. I'm going to share again here my desktop. All right, so you should see my desktop. And I'm going to start a new script to make a movie of a spinning Earth. So this is going to be a PS coast or a coast command that you all know. So GMT, oh, sorry, I should be good here and say I've been, oh goodness, /bin user. This shouldn't take so long time. User bin env bash. I think I finally got it correct. And I'm going to make a simple GMT begin coast plot, GMT coast for the whole world using the orthographic projection. I'm going to start off by centering it on Greenwich and 30 north. And I'm going to make it 12 centimeter. Why 12? Well, because my paper size is 24 centimeter by 13.5. So this is going to be sort of, will fit in that space. I'm going to colorize it burly wood, which is the only color that I like. And I'm going to draw grid lines because it's going to be like a 3D planet. And I'm going to color the oceans tomato because that's a good color for oceans. If you don't like my color choices, you can just replace them at whatever your colors like. But these are the ones I'm going to stick with. And then I'm going to center the plot in the middle of the paper, minus XC, minus YC. And GMT end show. And I'm going to save that script to earth.sh. It already exists. Yeah, because it does. There it is. And there's nothing new here, right? You've made this plot before. I'm going to make sure I didn't screw up anything by running it. And I got a beautiful map with a tomato ocean. Can you see this? Can anyone confirm that this is actually showing? Very good. Yeah, very good. Okay. All right. Yes. Beautiful plot of the world. This is a PDF. It has no name, GMT session.pdf it says, because I didn't name anything or nothing. I just want to make sure that I was capable of plotting a globe. Now, if we wanted to automate this and plot it again and again and again, we will get Einstein's solution of the same plot, right? Because there's nothing that changes in here. And that's because I have a fixed longitude of 0 for all time, right? Nothing going to change in this script. So we're going to make a few changes here. We're going to have this thing changed with the frame number. Now, the frame variable I think I called it capital movie underscore frame. And if I can spell it correctly, it will be even better. Movie frame. All right, so all I did was to say, okay, that part of my script, the longitude, I want that to vary with the frame. And it's going to just be a 1 degree change because movie frame is integers, right? Well, what if I want it to be every 0.2 degrees? Well, then we have to do other things, but the same principle. We're just going to have that thing be the variable. So now I'll save this. And of course, I can't run this on the command line down here because I can do it and it's going to get errors, right? Oh, because movie frame is not defined. I can't run it. So what I'm going to do is I have to run this as input to the movie command. So the movie command in GMT takes a script like this, and it's the one that replaces these variables with actual values. So I'm going to type those as comments to my main script here. So the GMT movie command will look something like this. GMT movie. And it needs to take a script. Well, that is our earth.sh. That's the input to movie. It takes a bash or a C shell or a Windows batch file as input. We're going to specify this canvas of what is the paper size and what is the dots per inch. How big is this screen? Well, I said we're going to use 360p, which is a 16 by 9 window with 360 raster lines, because everything's going to be rasterized to a PNG and then converted to a movie. I said we just should do the first 91 frames. So minus T can be set up to give how many frames do you want, and then you get 0, 1, 2, 3, 4, 5, and so on, or some other way of specifying time, for instance. But I'm just going to do it as a frame counter. The first time you make a movie, you shouldn't make a movie. You should just try to make one of the frames because you're likely to screw up something. I do it all the time. So I'm going to say the movie format should be none. I don't want a movie. I need to name the movie. I'm going to call it Earth. So the product's going to be earth.mp4 or something maybe. And I need to, well, what I want to do is just to create, we call it a master frame, just a single frame from the movie. And I want frame number 55, which should be about longitude 55, right? And I want that as a PNG plot. All right. So if I run this command, I'm going to copy this command. I can't run this script, right? Because this is just going to crash like I just did. I'm going to run this command down here, and it will read my Earth file, earth.cell, not create any movie, but just run it once for movie frame equals 55 and make a PNG. Okay, so sorry, I have an old directory called Earth. Be gone with you, Earth. Pretend you didn't see that. Okay, so I'll run this command. And, well, that's, okay. This happened yesterday too for me. It doesn't want to display preview. I have to actually kill preview. There we go. Earth.png. Okay, here's earth.png. So you can see it has the paper has 16 by 9. It's sort of this small PNG. It's only 360 by whatever that is in the X. And it is centered on longitude 55. So that part seemed to work. This GMT movie command, run it once for this particular frame number. Okay. Did you guys follow to this point? So this is what I did. I modified my earth.shell script to use $ curly bracket movie frame and curly bracket as the longitude. And I ran this command in the terminal. That will create that single one. Now, if I had any problems here, like the Earth was plotting off the page or I got errors, I would fix them like I would from a normal GMT script, but everything worked. So I can now move on to make a movie. So when making a movie, we have to specify what format do we want. And I pretty much most of the time do MP4. Now that we got the master frame to work, I can take out the -M option. And I can make a movie for 91 frames. And I think I have to remove my Earth here, just in case. I will now let it rip, and it will now run and make 91 frames and create an MP4 movie from those frames. And my computer has 24 cores, so it will spread these 55 frames across the 24 cores. So it only takes a few seconds for me, depending on your computer. This is actually an old computer with many cores, so it's both fast and slow. And it is done. And now I have a file called earth.mp4 in my directory, and I can open that one. And QuickTime is going to open that up. It's very small. Let's see if I can increase size. Well, I can probably drag it. All right, I'm just going to drag it so you guys can see it. It's very low resolution movie, but look at that thing go. It spins and spins, and it stops at 91. So that's all it took. 3 lines of GMT code, and you have a sophisticated movie with beautiful colors, and and the rest is just making this more complicated. So that's really the essence of making a movie. Just you have to be able to write a script that makes that single picture on the piece of paper, and then figure out what are the parts that you want to vary. And it could be many things that vary. The simplest thing was just a frame counter, right? And that's limited to integer values. But I could create a data file that had whatever longitude and latitudes I wanted to be the center, and use the movie column 1 and 2 to be the longitude latitude. It'll be identical script almost. All right. So hopefully everybody got this movie to play and work. If not, pipe up in chat. I'm just going to do a few more variations on this theme. So I'll leave that initial one there and make a copy of my command. And what I want to demonstrate is that we can label this thing with a couple of built-in options. We have a -L option in movie that lets you add a hardwire label or elapsed time or the frame number and that sort of thing, or real time if you're doing that. And I'm going to add elapsed time, which is -LF. And every time you place a text in GMT, there's going to be choices like what's the font and what's the font size and where the hell does it go and all that stuff. So you can look at that and find modifiers, but I'm just going to take the default and run that command. Copy and paste that one down here. Okay, I forgot to tell you this. Please do -Z on these commands, because what that will do is after the movie is assembled, it will delete the working directory with all the PNG frames, because GMT will refuse to run it again if that directory exists. And that's why I had to delete the Earth directory. Okay, so if I do it this way, then I won't have to bother with that again. So this is going to still take another 6-7 seconds for me. And then we have a movie. I'll drag it down here. Now you can see I have elapsed time. I think it's frame. Time is 1 frame here. It's not real time. But you can see it has placed a running counter up in the top left corner that goes from 0 through 90, which is 91 frames. So that can be handy. And it by default goes in the top left corner, and I could place it anywhere, of course. I'll copy my command again. And this time I want to add a progress indicator. So a progress indicator is some little thing that graphically illustrates how far along in the movie are you right now. And I think we have 6 different kinds of those that can be configured with different color, size, locations, and so on. And it's done through the -p option. And there's a lot of things to explore there in the man page that shows all the various kinds of indicators. I'm just going to go with the first one that they call A, B, C, D, E, F. And I'm going to go with PA. And it's going to go in the top right corner, I believe. Actually, I don't like the tomato color for the ocean. I don't know what I was thinking. I'm going to do light, I guess blue. Oh, boring. Light blue. Okay, light blue it is. Save that. Run my script again. So 55 plots are being made and converted to PNGs and then assembled using FFmpeg, right? That's why that is a requirement to do the GMT building. Okay, I guess the blue is better as ocean color. Who knew? All right, so it looks like that. And up in the corner here, you can see I have like a pie wedge, a pizza, or one of the slices there, the red slice going to grow as the movie spins around to give you an indication of how far along have you gone. Okay, so that's cool. And you can place that anywhere, and there's many other ones, and you can change the colors as you want, of course. All right, the last one of these themes I'm going to do is to do the whole Earth. So that's 360 frames. And I'm going to make it a little bit more higher quality by going to 720 PM. So a couple of things are going to happen here now. I'm asking for 4 times as many frames. So it's going to take 4 times as long. But then each raster is going to be basically 4 times as many pixels. So this will take a little bit longer. Depending on your computer, I'm going to time mine. I'm going to say time, and then I'm going to run the command. And then we are hoping it won't take forever. It won't, because each plot here is very simple, right? It's just a coast command plotting the coastline. There's nothing major going on. So each GMT plot is done very quickly. And then once the frames, this took 22 seconds real time for me. So you can sort of measure that. Maybe you can beat that with your computer. I can open it. So now, okay, now it's much higher resolution because it opens up this way. I'm going to still increase it for you. Increase size, I think that doubles it, just so you can see it better. And now it should go the whole 9 yards or 360 degrees around the planet. You feel free to change the latitude on this thing. I've put 30 north, so you can show the North Pole. But if you're from the southern hemisphere, you might want to see the South Pole, that kind of sort of thing. All right, so that's all there is to it in terms of doing the movie. Now I'm going to go back to my slides here. I can find my slides. A couple more things I want to just show you. All right, you should see my screen on points versus events. So it was very simple to plot something static like that and spin around. But if you want to plot symbols, normally we would plot symbols using plot. The problem, of course, is that they will appear on every frame. You plot a star, it's going to be on all the frames. That's not fun. So typically when you do movies, you're actually displaying events, things that have a finite duration or start at a certain point. And that's very difficult to do in plot without lots of scripting. So solution to that is a program called events that is similar to plot, but it takes time column as well and options so that we can only plot the events that should be visible for a given time. And from 6.2 onwards, events can also plot some of these very complicated symbols that you see today as Mecha and Coop and Velo. So the difficulty with events is that they have a start time and maybe an optional stop time. Let's say the eruption lasted from 2014 to 2017, and you want to show some glowing volcano during that time frame in your movie. Or maybe it's an earthquake that happened, and then you want to have it linger on for some time and maybe go in the background or have it on forever. So to do this, we attach these life curves, if you will, to each event. So on this graph here, the green curve represents the typical life of an event. It has, and then we talk about the symbol size here. So it has 0 symbol size until the event happens. Then the symbol size goes to a normalized number of 1, and it stays at 1 until you either decide that the event ends and it goes back to 0, or you let it stay on forever. So it's just a step function. So that's the basic curve, but you can modify these curves to have the symbol start to appear slightly before the event happens and maybe come up with a larger size to announce its arrival, and then fade back to the normal size. And then maybe after the event is over, fade back to a smaller size and a different color. So these kinds of curves can be created on the fly for each event. And we have separate curves for the size of the symbol, the color intensity of the symbol, and the transparency of the symbol. So what we're going to work on as a group here is making a movie of Pacific seismicity for 2018, only showing magnitude 5 and larger. And again, each frame is going to give us a central longitude that we're going to build in this plot. We're going to plot the background coast plots that we've seen, and we're going to plot events on top, but only those that should be visible for the given time. So future quakes should not show up, obviously. And if all this works well, then we can consider replacing the PS coast map with a real GRD image and make it really fancy. So that's sort of what we're going to do. We're going to get the data sets from the USGS from 2018. And to avoid typing and errors in typing, you should get the script getquakes.sh from the GitHub animation folder and run it in the directory that you're working. So I sent that in Slack as well. So I'm going to stop. Sorry, I stopped the whole sharing. I stopped my presentation. I want to go to and share my screen here again. Desktop. Okay, so here's my Earth. So now we need to run this script called get quakes that you should have downloaded. So I'm just going to open it up here so you can see what it is. Oh, it's not there. Get quakes. So basically, I'm trying to run a command, GMT convert, which will get a URL. And the URL is complicated because I'm trying to pull out earthquakes from a database sitting in Denver, I think. So we will create this URL. We'll call GMT convert with this URL. And then we will pull out some columns that you need, like longitude, latitude, magnitude, depth. And I'm going to scale the magnitude by an arbitrary factor of 50 and pretend that this number that comes out is the symbol size of a circle in kilometers on Earth. And that's going to be quakes.txt. Then I'm creating a standard CPT file that is red, green, blue, depending on if it's shallow, intermediate, or deep quakes. And then I'm creating with GMT math here a time series for the whole 2018, one record per day, time units is day, where I'm basically creating longitudes that goes from 160 to 240 over that full year, one increment per day. So no longer integer frame locations. This will be longitude that varies smoothly from 160 to 240 during the time of this movie. So get quakes. I'm going to run bash get quakes. And that should then create files like times.txt, quakes.cpt, quakes.txt in your directory. Those are the files we need to work on this movie. So I'm going to start creating my script, user bin env bash. Actually, I should open the Earth script that I have there. I'm going to copy and paste a few things here. Let me just copy the whole thing for now and put that in. And I'm going to save this new one as quakes.sh. Replace what I have there. Okay, so we know this gives a spinning world, and that was fine. We're going to use the same spinning world as the background for the seismicity, but we need to make a few changes. So as I said, we're not going to use movie frame from 1 to some number. We're going to actually use whatever's in the file times.txt that I created. So the times.txt file that got created somewhere down here, it looks like this. It goes from all the days in 2018, right? And then it goes from 160 longitude, and then it inches away across the planet until it gets down to the end of the year at 365 days, and it's at 240 degrees longitude. So I'm going to reuse this file in movie and assign the second column here, which is column number 1, this is column number 0, as my longitude. So in Quakes here, instead of movie frame, I'm going to say movie col1 should be used as the longitude. And in fact, if I also copy the very first of the lines from before there, I can make a movie for a particular frame. I'm going to, now instead of giving it frame numbers, I'm going to give it the file times.txt, because that's the data file that the movie needs to know now about all the frames that I want to make. And I want to make none. And I want to make, again, like the 100th frame. Just want to see that that works for me. Quakes.sh. Let's double check that I didn't make any errors there. I did make an error there, correct syntax. Oh yeah, oh, brain freeze. Okay, so I'm going to run this command in the terminal. Sure, that already. Run that in the terminal. And that should create my quakes.png again. And now it's centered in the Pacific on longitude, whatever it is for frame 100. All right, so okay, so that part worked. Now we need to plot the events here. So we're going to do this with GMT events. And we're going to pass it the quakes that was created. Yeah, I'm sorry, I didn't show you that. So the get quakes script created this file quakes.txt. And it looks like longitude, latitude, depth, and then a symbol size, magnitude scale by 50, and then the time of the quake. because events need to know the time, otherwise it has no way of showing which quake should be valid. So that's the file format we use. And then we're going to run the command quakes.txt. We're going to color the quakes based on their depths. And that was what the quakes.cpt file is used for, that get quakes created. So quakes.cpt looks like this. It says, be red from 0 to 70 kilometers, green from 70 to 300, and 300 to 1,000, 10,000. That's way beyond the depth of the Earth. Be blue. So that's the coloring scheme. And then we got to tell it what is the current time. What do I mean by current time? I mean the time of the frame. Well, there are a lot of frames. Well, what is the current time of the current frame? Well, it is given by the first column in the times.txt file, right? That is movie called 0, the first column. So when we run this script, we want it to happen for that time and which quakes should be present at that time. The symbol we're going to plot is an ellipse, and it's going to be a degenerate ellipse. So that is a circle. So minus S, capital S, a hyphen does that. And then we have to specify that the time units that we are using is days. And so it should get the right symbol size. There's no symbol size given here, so it will read that from the file. That will be the scaled magnitude times 50. It will read the depth and use the quakes.cpt to get a color. So we should get colored circles on the Earth here. I should have tested this particular thing before we did this. I'm trying to see if this will give me a default plot. It may not. Quakes.png. No, I didn't plot anything. Too bad. I'm gonna have to fix that so it works. Because normally we'd have to give a bunch of options here to specify. And that's going to be these timelines that's going to scale with each event. So we need to specify the sizing. So the sizing, so these options are a little bit complicated, unfortunately. But events and movie are very new tools, so we hasn't gone through a lot of testing, I guess, or finding out what's the better way to do some of these parameters. But right now we can specify this curve in different ways, and I'm going to have it start. So the events should start showing up 2 days before and grow, and then I want to have a decay over 6 days where they go smaller. I want the size to initially be 5 times larger. And then when the event finally fades away, I want it to go to 0.5. And the transparency, actually, let's see if we can get away with this for now. So that means the symbol should start to rise up 2 days before the event, and then it can be a delay of 6. And I will try to run this. Okay, I should take off my show here since preview doesn't like me. All right, well, that I like though. So by just specifying that I want the symbols to start 2 days before the event time and then decay later, you can see that I got some symbols. So these are the quakes that happened within 2 days of the current frame time for frame number 100. Okay, so that's positive. Now, what we're going to do in the breakout is to try to modify this command here a little bit And what you should aim for is to try to change the intensity of the color. So when it comes up, it will go a little bit white. You do that with -mi. Look at the syntax for how that works. And then we want to have the transparency go down at the end when that's done with an MT option. And there's some arguments that follows these two. So I think I'll stop there and we can go into the break and work on this script further to try to get this working. And remember also, you can make this to run the movie by switching this to MP4 and take out the -m option. So those are the two sort of basic ones. And then you can add these other modifiers to add time and progress indicator. Okay, so I'll stop that for now, and then we'll try to give this a shot in the breakout room. Okay, good. Just my settings. All right, it is, what is it here? 8:55 UTC, and we are starting in the final project session. So for this workshop, a final project is very individual. What we would like you to do is to use data that is relevant to this kind of workshop, so geodesy data, seismicity data, and make a nice looking, I think, publication quality GMT illustration that you can imagine being, you know, figure 5 in your thesis or your paper or something like that. And it can be almost anything. It shouldn't just be a PS Coast, you know, one-liner thing. It should be something that uses, you know, a data set that you're working on as part of your thesis or your project, and looks nice and is, you know, will pass your advisor's filter or the journal editor's filter of, you know, nice figure. But beyond that, it could be almost anything. We're not going to prescribe too much on that. You can start working on this now in this session, and you can get help from us in the room on, you know, details. And then I think you have until, it's the 28th. I can't remember now. I'll have to look at the schedule here. Maybe someone can confirm when the final projects are due. And what you do is you post them on the Slack channel, and we probably should have create a channel for that. Would be helpful for final projects. If we don't have it, then we don't have it. And so you post that final plot, and by that deadline, then you get credit for having passed this course. So that's how we're going to do it. And we are available, you know, to answer questions on Slack between now and then as well. But, you know, not every day, all the time, but we can address that kind of issues. Any of the other instructors want to pipe up and say anything about this particular task, or did I cover the basics of it? This is my understanding of how we did it last year. It's pretty flexible. So instead of just you doing what we tell you to do, you make a figure that you want to make based on your data or area and so on, and take inspiration from what you learned in these 2 days, and try to put this into a good use so that you can use figures like this in your publication defenses and whatnot. You could, of course, also make a movie as part of this project. I know the movie thing is sort of a little steep learning curve in the beginning, so it's very hard to go through and do a lot of stuff in the short time allowed, but that's an option if you want to. And I think Federico is going to share, might already have shared, a link to his YouTube's page. He has done a lot of cool movies, so you can get inspiration from our channel and his channel on how to make GMT animations. Once you get a hang of it, it's sort of addictive. You want to make more.
I have a question.
Yeah.
I think that using GMT, we can also plot 3D maps, right?
Yes, to some extent, yes.
Yeah, so could you share the links for using some kinds of examples for 3D plots in GitHub or somewhere else, I don't know, or documentations or something else?
Right. So there's just be clear. So what we do in GMT tends to be what we call 2.5D 2D plots, where we show a surface, for instance, topography in XYZ dimension, but we're not doing volume plots or anything like truly 3D in GMT. So the examples gallery will have a few examples of what 3D plotting in GMT looks like, but it doesn't do volume rendering and things like that.
Oh, okay. Okay. Thanks.
Yeah, sure.
The tutorial, one of the last section or something of the tutorial also shows an example of how to make a GRD view. Probably is what you are asking for, not a sphere drilled with holes, or that type of things. GMT does not do yet.
Yeah.
Well, might.
So if it's plotting 3D topography or something like that, yes, we can do that. If you're doing mantle convection and you want to show flow in the mantle, no, we can't really do that. We can do cross sections to some extent, but not volume rendering.
Paul, could I ask? I've been studying the GMT events module, and I'm struggling in the movie business to understand really what events is doing. Is events a wrapper to somehow to PSXY, where it's you're calling it inside move, or it's called in conjunction with move. I don't understand what events is doing. Could you explain it again?
Yeah. So imagine we're making a movie that goes from 1 to 100 in time, let's say, right? So you're going to make 100 plots. Right. Let's say we pick one frame at frame 30. At that time, you want to plot the symbols that should be visible at that time. So no future quakes, but past quakes in some sense. So what events does is to read your entire catalog of events, throw away those that haven't happened yet, and just look at the ones that should be plotted. And it will apply these 3 functions, the time functions of symbol size and intensity and transparency, to that data set that remains, depending on the time. So if it's before the event happens, maybe it will be at a small symbol size. So it creates files that plot PSXY, if you will, can use. And then it does a call to the plot module to actually plot the few symbols that needs to be plotted at that time.
Okay, and then some of these flags, then you said the magnitude, which is a function of size. So like if you wanted, but event, the fadeaway time, is that the minus E option?
The minus E option is the first one you will sort of study. You can see, that's how I draw the symbol size over time. So I call it the rise time. There's a plateau time, the decay time, and all those are optional. The normal is sort of just on and off step functions. And then I can have a little fading into what I call a coda, where the symbol doesn't really go away, but it has a small symbol size. So you can control all those things with the minus E option, and then you can add these intensity and transparency effects with the other one. It's a little tricky stuff. I have to read this man page myself, and I wrote it, so it's not easy. But once you get the hang of it, it becomes quite easy and very powerful. But like any GMT command, it's a learning curve on how to do it.
Coast, got it. So coast, then you're calling it in the conjunction with movie. All right, got it. Okay, thank you. That helps a lot. I was studying it, and it's a new concept, and it wasn't clear.
Yeah, sure. Events makes very little sense to run by itself, but it can, and we can. We have examples of just running it for a static figure, which will show what happens, for one frame. But it only makes real sense in the context of the movie.
Yeah. Okay. Thank you.
Yep. You bet. Yeah, so I got a question in Slack here, what we're actually supposed to present next Monday. So it won't actually be a presentation. It will just be you submitting your final figure to us through Slack. And the bar is very low. We will probably have a bar that says, if you just send us a PS Coast plot or something at the last minute, then that's not passing the class. But if you send an earnest effort of making a nice figure with your data, having done that by the time, you will pass the class, right? But there won't be a presentation because we are, too many people to go through a formal presentation. There's a lot of people offline that are not actually on the Zoom. So just submit your final figure by the final time, and you'll be good. And Melissa has created the final products channel. So we just need to add that to our Slack by browsing the channels and then adding the final product, joining that one to your Slack application. And so please drop them there. Then it's easy for us to find and keep track of who has and who hasn't done it. And it will be on you to make sure you submit it by the final time. We probably aren't going to be motivated to hunt you down and remind you that you only have half an hour left. It's up to you to maintain control of your life. We have other things to do, I'm sure. Any other words from the instructors about tips or things, anything before I guess we'll break into breakout room, and then people can start working on the project and get some more guidance from the instructors until we run into the wrap up, and then we'll meet again during the wrap up and do the usual sayonara and thanks and that kind of stuff. Okay, so let's break up into the breakout rooms again one more time and work on our projects or get ideas to discuss what we want to do. All right, we are all back in the plenary section. Those who are still awake, I know many in further east than me have bailed, and it's understandable. Here it's not even noon yet, so I don't understand. It's a problem. All right, so I just want to say first thanks to the instructors who were willing to do this with no pay, no gratitude, no pat on the back, no t-shirt, no coffee mugs, nothing, just showing up and wasting their evening when there's perfectly many other things they could be doing. So thank you guys for helping. And then second to Melissa and Junauko for helping arrange the whole thing. This is great that she takes care of everything for us related to recordings and breakout rooms and whatnot. So that makes this really, really easy for us to do. We just need to babble on the things we can contribute to. And then thanks to all you guys who actually decided to spend 10 hours with us, banging your head against the brick wall of GMT usage, and then still be smiling. Well, I don't know if you are. It's hard to see. In the moving forward. So thank you for participating. As we said earlier, in terms of the final project, it's pretty easy. You just make a publication quality type figure that you're proud of, and you submit it to the Slack channel by the 28th, and you will pass the class. So that's pretty straightforward. You can ask questions to us through the Slack channel. It will be up until the course is all over for sure. And beyond that, there's the regular GMT forum and GitHub for bugs and all that stuff. As you start using GMT more, if you have suggestions for improvements or you find problems, please tell us through the channels, forum and GitHub, so we can fix it. And also think of yourself as part of the community. You we giving you these things, you can help a little bit too. There's a lot of people who know way less than you that you can help by answering some newbie questions on the forum, and just to be part of the community and help us grow and maintain GMT and make it better for everybody. So I guess that's all I'm going to say this late hour, unless any of the instructors want to end with a good joke or anything. No, I think we're all tired. Let's go get some coffee or sleep or breakfast or lunch or something. Okay, so thank you guys. Make sure you submit your thing on Slack by the end, and I'll see you next year, some of you at least. Sayonara. Checking out.
Yeah, thanks, Paul.
Thank you,
Thank you,
Leo.
Paul.
Thank you all, guys.
Everyone.
Thank you.
Thanks a lot, everyone. Very nice. Thanks a lot.